away from Earth, 1,000,000 miles, or 1.5 million kilometers, but it has this very special orbit, and it can be cold and dark and really, really great for astronomy. So there's just this collage I picked out, which captures the size, how it's much bigger, how it has a very special orbit. And there you see the Webb telescope in artist's conception. It's so big, it just doesn't have like the cover around it. And instead it has this giant sun shield, this 5-layer, extremely special sun shield. And perhaps some of you followed it as it was being tested. Look how big it is. It's the size of a tennis court. It had to be all folded up and opened up and not get tangled. And that's one of the reasons why people were so worried about the whole thing. In fact, it's sort of old news now, but the way that the Webb had to, it was so big, right? It is so big. It had to be all folded up to get stowed in our rocket fairing and launch, and it had to unfold and had all these really key important steps. And people are just absolutely thrilled that everything worked out. I'm going to get to some results in the moment, but I couldn't help but want to recommend this documentary called The Hunt for Planet B, because this film was made by Nathaniel Kahn. He is, and he took footage like 10 years before now, and he followed around parts of the telescope and people as the telescope was being built. He's got some fantastic footage. And it really does try to tell part of the human story behind the telescope. Why are we doing this? How is it built? What are the things people lost sleep over? And this whole movie was made all before the Webb launch. Well, last fall, I got to go to New York City for a night with Nathaniel Kahn and about 15 people from the movie. They were either in the movie or they made the movie, because this movie was up for an Emmy Award. So we go there, we showed up there was like a pre-party before. We got there right on time, which apparently only like the nerdy people do, because as the 2 hours went by, that's when the sort of people super dressed up showed up, who are probably, a lot more famous. So then we moved to this auditorium that was all fancy with lights and colors. And it was like a high school graduation or the university graduation. Honestly, it really dragged on, because they don't tell you what order yours is going to be called. And in every category, there's 5 films. And what they do is they have a big screen and they show like maybe a less than 1 minute clip from each film. Then they pull out the envelope and nobody knows who's winning, not even and they then tell you. So all this was happening. Finally, it got to ours. Our row of people was really, really excited. They showed them all. Then they called us and we won the Emmy. And it was like a huge, exciting moment. And there's Nathaniel, the person who made the film. And you can see behind him all the Emmys lined up. Like, come on, look. And the funny thing is, none of them are engraved in any way because they don't want anyone to take a sneak peek. You can see all the people we were with. There's me in the front in red, and in the back, some of you know Charles, my husband, who was also in the film. So I do encourage you to see it. It has a lot of different messages. So now I'm going to get to some science, and now I have a couple of slides that I do need you to pay attention. Because if you don't know about this yet, this is how we're trying to find signs of life in the atmosphere of an exoplanet. And what I'm showing you here is a cartoon diagram of a planet going in front of the star as seen from our telescope. How many of you have seen a diagram like this before? Okay, so about half of you. So some of you haven't seen it, but one of the main ways we find planets today is we're looking for a tiny drop in brightness in the star as the planet goes in front of the star. And we don't see the cartoon on the top. All we see is like a point of light, like one of these lights up here, just a point. But if we look at enough stars for long enough, we'll get lucky and we'll see that some planets whose orbits are aligned just so, the planet goes in front of the star and the starlight drops by a tiny amount. And that amount is the ratio of the area of the planet to star. And that's what you're seeing on the bottom. You're seeing the relative brightness as a function of time. And you can't read the numbers, but don't worry too much about it. You're seeing a star, which is just doing same brightness. It's like as if you took your camera, your phone, and just like click, 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 minute after minute for hours and days on end, until you see this tiny little drop in brightness. And that's a planet going in front of the star. Now, that's just me telling you that. There's decades of work behind this, and there's now the TESS Space Telescope. I used to play a leadership role on that telescope. It takes a lot of people a lot of time to figure out that that's the side of the planet, okay? But for now, you just have to believe me. A planet's going in front of the starlight drops. When the planet finishes going in front of the star returns to its normal brightness. And this drop is pretty small. It's like 1% for a big planet, but it can go down to much smaller for a small planet. So I hope you understood that part, because what I'm going to tell you next is the real kind of, for lack of a better word, the secret sauce. So I want you to think about the planet now. There's an exaggerated size of a planet. It's got a dark part and a gray part. The gray is representing the atmosphere. It's all very exaggerated so you can see it, okay? So I want you to imagine now that, that the way we detect the atmosphere is the starlight shines through the atmosphere, and some of the starlight gets blocked, but other parts of the starlight don't get blocked. Like a cartoon image of a flashlight shining through a fog, some light makes it through, some doesn't. Let's imagine a wavelength where the planet atmosphere is completely transparent. No light is blocked at all. Then how big is the planet in that case? The planet is the size of the black disk. So there's a small drop in brightness. Now let's think of a wavelength where the atmosphere is opaque. It now blocks all the starlight. Now how big does the planet look? It's a tiny bit bigger. Now it's the black plus the gray. These sizes are all exaggerated. So what we're trying to say is the planet looks a tiny bit bigger at wavelengths where the atmosphere is strongly absorbing. Well, the good news is this talk is recorded. So if you want to understand that, and I went too fast, you can go and watch the recording. I do teach a class on exoplanets, and we don't spend 2 minutes on this. It's more like 2 lectures or more. But just think about that for a moment. We're taking a transit at different wavelengths, and we're looking for a drop in brightness that's larger at some wavelengths than others. So whether or not you understood that, you can still enjoy this. This is the James Webb Space Telescope, real data on an exoplanet. And what you're seeing is the brightness on the y-axis and the time on the bottom axis, time from mid-transit. And you can see on the top right, it's showing you the wavelength. That's why it says W, and this is in microns. So even if you're not technically oriented and you don't understand this, you can still look and see where do the colored points drop beneath the model. The model is the black line. So most of the time, the atmosphere is pretty transparent, but at a certain wavelength, the atmosphere is opaque, and these colors drop down beneath the model. I want you to shout out the number if you can see it. It's kind of hard to watch everything going at once.
446.
Okay, we have a 446. Yeah. Okay. There, see it? Let's try it one more time. So this is real data, and someone just put this together, and look, the planet is about the same size all the time except there. I mean, that is wow. You can see by eye, the planet is a tiny bit bigger at a certain wavelength. That's just amazing, honestly. If I could kind of unpack the whole last 3 decades of exoplanets, and the fact that we can see this tiny change in size of a planet by eye is just stunning for us. So if you didn't understand all this, please go back and watch the talk. I just wanted you to see that the data is so beautiful and amazing. And we have a slightly different way now to put the data together, okay? So now I'm switching from transits at a different wavelength to just now amount of light blocked per wavelength. This is something a bit different now. We're now asking ourselves how much light is blocked as a function of wavelength. So it's amount of light blocked on the y-axis, and the x-axis is wavelength now, not time. So if this atmosphere didn't exist, or the atmosphere wasn't visible, the planet would be the same size at all wavelengths. And the points are the data, and the blue is the model. So if the planet atmosphere was not showing up here, then all this would be as a straight line, because the planet wouldn't be changing size as a function of wavelength. So to believe we've detected the exoplanet atmosphere here, all you have to do is agree with me that this is different from a straight line. And wow, this is so much different from a straight line, right? I mean, even a child surely could. There's like one child here, little child. Is this a straight line, or is this like a big curve? It's wow. I mean, when people saw this, they weren't expecting this giant feature of carbon dioxide. So now, just getting a bit more technical for the people who are studying science here, you can just read this, but this is a hot giant planet. This is not a planet we're looking for life on. It's too hot for life. It has a giant, like, hydrogen helium atmosphere. And in this wavelength range between 3 to 5.5 microns, which, by the way, it's hard to observe that from the ground. Space is amazing for it. You're seeing this tiny drop in brightness that corresponds to this atmosphere. So this carbon dioxide, by the way, it's not the dominant form of carbon in this planet, but it's a very strong absorber. You know how on Earth, we're worried about our carbon dioxide increasing by parts per million. It's a hugely strong absorber. And here it is on this planet. Now, we, meaning the community, has a bunch of planets being observed, their atmospheres being observed by the Webb telescope. This is probably the main, there are a couple other results out, but it's really just getting started now. So you'll have to probably wait a few months, a year, to see where this is really going. But I'm now going to jump ahead to terrestrial planets, small exoplanets, because that's what we want to do with the Webb telescope. And I want you to all know that we can't study true Earth twins with the Webb telescope. I'm showing you a real image of our sun on the left with a fake Earth. And on the right is a small red dwarf star, tiny, tiny, tiny star with the same size planet in front of it. And what do you notice? Well, the small star there, a lot more light will be blocked by the same size planet from the small star compared to the large star. And I want you to think of the atmosphere now, like the atmosphere being like the skin of an onion on an onion. Well, wow, observing an atmosphere, a small thin atmosphere against the backdrop of a sun-like star, we're not there yet. We can't do that. But we can observe an atmosphere of a small planet with the backdrop of a small star. So, by the way, in that sort of spirit of crazy to mainstream, before exoplanets were found, people hated small stars. They thought they were the worst thing ever for a terrestrial planet. For a lot of different reasons. I'm going to come back to some of those in a moment. But for now, it's all we can do. And so we're doing this. Now, if any of you heard of this system, TRAPPIST-1, it's a really famous system because this TRAPPIST-1 star is so small, and any smaller and colder, it wouldn't be a sun. It wouldn't be able to have support fusion in its core. Okay, so let me, to just tell you how different a planet around an M-dwarf star would be compared to an Earth around a sun, let's take a little mental break and go on a virtual trip to a planet orbiting a red dwarf star. This is an artist's conception. And the first thing you notice is, well, the artist took artist license to make the sky a different color. We don't know what color the sky would be. We could maybe, make models in our computers and come up with a range of answers. The other thing they're showing you is that for planets that are the right temperature for life, they're much closer to their star than Earth is to our sun, because the small stars give off only a tiny little bit of energy. It's like the campfire analogy. A small, tiny campfire, you'll have to stand very close to keep warm. So for a planet really close to the star might have to be big in the sky. The artist is also showing you these other planets in the same system. The thing I like most, actually, about a planet orbiting a red dwarf star is over time, they will have evolved to be in a very special configuration called tidally locked. Just like the moon shows the same face to Earth at all times, the planet gets into a situation where it rotates one time for every time it orbits. So 1 day equals 1 year. And if we could visit this planet, we'd notice something really odd, that one side of the planet is always in day and one side is always in night. So where would you go? Would you go to visit where it's always day? Some of you are saying yes, no, twilight. No, wrong answer, because you're here for an astronomy thing. You go to where it's nighttime. But imagine you could go where the sun is always setting, right? Or has anyone heard of the green flash? I would want to go and just see, like, this green flash, this phenomena happen all the time. So it would be really weird if you're a child here in the room. I want you to know that 1 year on these is quite short, because the closer a planet is to the star, the faster it goes around. So a year could be as short as 10 days or shorter. So your birthday would be every 10 days. But I don't think your parents would be too happy about that. That would just be, I think probably they'd celebrate on centuries. Yeah, so that every century, that would be every 100 years. So these planets are different. I mean, they're probably people on those planets thinking about us going, it's so crazy, they have day and night. You know how nights are so long here? I mean, they're getting a bit shorter now, right? But it's, real drag. They don't have it on those worlds. But seriously, I was just trying to be a bit funny, because the serious problem about these stars is they give off flares, lots of flares. And here's a real image of our sun taken from a satellite showing our sun with a flare. And this is taken at a narrow wavelength, so the sun looks all mottled. But what's really crazy is that all stars have flares, but these M-dwarf stars tend to have stronger, more frequent flares, lots of flares. And these flares are, they wouldn't probably harm life actually. In fact, we had a giant flare event here on Earth, the Carrington event. Has anyone heard of the Carrington event? In the 1850s, there was a huge flare and part of our sun came off our sun and came hurtling towards Earth. And that part had an embedded magnetic field, which hit Earth's magnetic field and induced a current. And our Earth literally became electrified. People saw the northern lights all the way down to the equator. They claimed you could step outside, like here in Toronto, you would be able to step outside and read a book by the northern lights. Like it was insane. Telegraph wires caught fire. There's actually a really good book. It's called Aurora. It came out recently. It's going to be made into a movie. And it describes what would happen if that happened today. Because now we have a giant power grid. I think we're okay in Canada, because do you remember the event I'm getting like way off track now, but remember in the late, those who were around in the late 1980s, we had like some satellites got knocked out, our power grid had a problem. So supposedly in Canada, we're all good, like with the equivalent of circuit breakers on our transformers. But this book takes place in the US where they don't have that. And it's like a different type of pandemic, basically, because everything's knocked out. So I want you to think about TRAPPIST-1, where people have observed that every 80 days, it had 40 flares. And one flare was as energetic as the Carrington event I just described. So imagine we're on a planet like that. I think I know what would happen though. It'd be like when you get I don't know if we still have snow days here in Toronto, but I think it would be like a snow day where a flare is coming, everyone has to go in your special basement for a day and just kind of stay there and everything's canceled. So when we had our Carrington event, no one died, but it's a really big problem. It sounds funny to you, but it actually might kill our ability to find biosignature gases. And myself and other astronomers now, this is like the most forefront thing I can pass on to you. And I am sorry it's bad news right now, okay? But the problem is that the background star, the planet's going in front of the starlight's shining through the atmosphere. We're trying to measure the tiny signal. The problem is if the star itself is changing, because it's the flares, not the flares necessarily, but activity means there are spots and those spots are evolving and the star is rotating. And this is really confounding because the background star is not uniform, but these little tiny changes, they're actually bigger than the atmosphere signal we're looking for. So yeah, it's kind of bad news, actually. And people are now really busy trying to work hard to find out, can we model the signal? Can we remove the signal? How do we deal with it? And TRAPPIST-1 has been observed. There's, I think, one paper out already, no signal. I'm part of a team that has data coming up in the summertime on TRAPPIST-1e, actually. And we have 4 transits, and we are really hoping to see the big carbon dioxide feature to say at least we've seen the atmosphere. But this is a really huge challenge for us, and we kind of expected it. And one of the reasons people didn't like red dwarf stars before for life, habitability in life, was because of this activity. So that activity is kind of in our way. And I just wrote a few scientific notes here that there's maybe a few to half a dozen rocky exoplanets in the habitable zone of red dwarf stars. We want to know, do these planets have an atmosphere? Can we find water vapor, then possibly biosignature gases? But right now, the star variability is preventing us from making those measurements. Okay. So let's just imagine now we did have the capability of finding trace gases and looking for signs of life. Well, what gas would we look for? There's oxygen, of course, but our own Earth only had oxygen for half of its life. And for a lesser time was oxygen abundant enough in the atmosphere for us to be able to detect. So I like this question a lot. I mean, there are a lot of gases that are sign of life. That's like if you left something in your fridge, sometimes you're a bit lazy or in denial and you don't want to clean it out. It gets moldy and smells bad. That's technically a gas, a biosignature gas, a gas made by life. It's like when you go into the forest and the beautiful smell coming off the pine trees, that's a gas made by life. There's thousands of gases made by life here on Earth. And we do call a biosignature gas one that can accumulate and in the atmosphere of a distant planet, one that we could someday somehow detect with our telescopes and possibly attribute to life. So now I'm moving on to part 2 of my talk, When I worked on this for like a decade or more, my team has been doing this kind of chemoinformatics problem where, like the squirrels collecting all the nuts, we collected all the different molecules that could exist, those that are made by life. We have this kind of giant framework we're doing a lot of different projects on. But one of them was to go through and ask what gases could be signs of life. And one of our favorite gases that we hit upon almost right away is the gas phosphine. Phosphorus is an element essential for all life on Earth, but it's used by life as phosphate. Phosphine, that's a phosphorus atom attached to 3 hydrogen atoms. It's incredibly rare here on Earth because we have almost no hydrogen, but we have a lot of oxygen. So phosphorus is primarily in the form of phosphate. You know, on Earth, we humans make phosphine as pesticides and things like that. Life makes phosphine in oxygen-free environments. It's found in animal guts and wetlands. So over penguin colonies in Antarctica, penguin poop, lots of phosphine. So I was working on this. My whole team was working on phosphine and other gases. When we learned about someone across the globe, some of you know where this story is going. We learned someone across the ocean, Professor James Webb, was also working on phosphine. And she was actually trying to find signs of life on the planet Venus. And when we sort of go to, UFOs are really crazy, it's kind of good we had that talk before, because looking for signs of life on Venus seems cool, like all good. And in fact, it is kind of crazy, but we do support like going out there and looking for evidence and pushing the boundaries. And I do like the phrase, the line between what is considered mainstream research and what is considered crazy, that line is constantly shifting. And just like in the UFO case, I'm not gonna be able to give you all the facts today, so you need to go and read about this and make up your own mind. But just when you read, try to be objective and don't just get the one that sort of goes off in one direction. So Professor James Webb also came across phosphine as a really unique gas that on Earth is very unfavorable energetically. It's not just lying around, but it has to be purposely made and is only associated with life. She proposed to use some radio telescopes to look for phosphine on Venus, and I'll come back to that in a moment. Let's just talk about Venus now. Why is it so crazy? Well, due to a massive carbon dioxide greenhouse atmosphere, the surface of Venus is too hot for life of any kind. But if you hike up a mountain, it gets colder and colder. And so too on Venus, such that 50 kilometers above the surface, it's actually not too hot, but just the right temperature for life. And oddly enough, up in the clouds of Venus at those layers, it's the same temperature and pressure. And so for over half a century, starting with Carl Sagan, people speculated that perhaps there's life up there. Now, did you know our own Earth has an aerial biosphere? Bacteria from our surface get swept up and they go into cloud particles and they stay there for maybe a week or two before they're rained back down. But on Venus, interestingly, the clouds are permanent. They are always there. They are vertically extensive. They're like 20 kilometers deep. And so this idea of life in the clouds has persisted for a very long time. But it's not all good up there. And the reason why it's so controversial is we heard about water in the first talk. Water is really important. There is water in the cloud particles, just a little bit, but it's locked away to the main component of the cloud, which is sulfuric acid. I don't suppose there's any chemists in the room, but sulfuric acid is a nasty, I don't know if you've got to use sulfuric acid in anything you've done. Have you used sulfuric acid in anything? Got to ask your teacher or professor about that. It's a nasty chemical. It will destroy life. If you dropped it, like it would burn a hole in your clothes, in your skin. It pretty much kills everything we know about, most things. And so this is really, really bad for life, at least life we know of. So Professor Jane Greaves invited my team to work with her because we were also working on phosphine. And I'm not sure how many of you heard about this, an announcement of a report of phosphine on Venus. This was in 2020 in the fall. And we reported a detection of phosphine on Venus, a tiny, tiny amount, like the level of tens of parts per billion. And we said that, hey, it's a mystery. Just like on Earth, there's no hydrogen, little hydrogen. The temperatures and pressures are very unfavorable for phosphine. We wrote 100 pages of all the things all the ways it might be produced: volcanoes, lightning, meteor delivery. And none of these could match anywhere near the amount that we had reportedly detected. So that leaves room for the possibility that there's life in the clouds of Venus making phosphine. So how many of you thought that was relatively logical? found a signal, worked through all the possibilities. It wasn't there. Maybe it's life. Yeah. Well, people were furious. The whole world seemed livid about this. And they had a lot of different reasons, but one was just unexplainable. I should have my own sociology slide. I don't know what it was. People kind of got on Twitter, emailed groups saying there's can't be phosphine. We all know Jupiter and Saturn have phosphine. Well, they do, but they also have a lot of hydrogen. And beneath their atmosphere, it's super hot and favors phosphine. And phosphine can come back up through convection and other means. So that was one story. But then, unfortunately, the data is all public and people analyze the data. And many teams did not recover the signal. Some teams did recover the signal, but wanted to attribute the gas not to phosphine, but a different gas called sulfur dioxide. So that's how science works. It goes back and forth. This story is kind of still ongoing. But the phosphine story, although it's still kind of controversial, it's still living on. It led to a whole other flurry of activity. You would not believe the kind of things that are going on now. And I get to the point that's most relevant to the theme of the sessions tonight. It's kind of life as we don't know it. I don't know if there's life in Venus, okay? I don't know if there's life there, but I do know there's really, really interesting chemistry. And there are several chemical anomalies, atmosphere anomalies, puzzles that have been around for 4 decades. So it's not just this controversial detection of phosphine, it is tiny amounts of oxygen that were measured in the atmosphere. The USA sent probes to Venus, a probe that split into 4. The former Soviet Union, they sent like over a dozen probes that went through the atmosphere and made measurements. So some of these measurements were made independently. Some measurements are made from here on Earth. But there's reported tentative detection of ammonia, like phosphine. That one is really unusual and shouldn't belong. There's tiny amounts of oxygen presence. And there's also major depletion of sulfur dioxide and water vapor in the clouds. This is getting a bit too technical and the night is wearing on. So I'm going to just jump ahead to some, maybe like what I really want you to, a couple of things I really want you to know about. So I'm going to skip that one on the left. I want to talk to you about something on the right. Do you remember from, now I don't know, it's been a long night, but in the first talk, Dr. Rothschild was talking about people trying to like make life from scratch in the lab. We're not trying to do that on Venus. But we are trying to change people's minds about sulfuric acid as a solvent. It turns out that in planetary science, people have kind of adopted, okay, I just have to make a joke. I don't know if you're going to get this. I'm starting to feel like the UFO guy because so I'm just like, all the people think sulfuric acid could never support life, honestly. Once I had my son during that pandemic summer when there were no jobs, the sports fields were all closed. There's like nothing for a high schooler to do. He worked on the Venus project. He wanted to do real experiments. And we found out you can't order large amounts of sulfuric acid to your house. But you can order a lot of little bottles. So you ordered like 30 little bottles. And he was supposed to test various, spacecraft material like and other things. We had to do it in an outdoor lab because again, all labs were closed. We made up an outdoor lab. And what's the first thing you would put in sulfuric acid? Some of you are like close to being, you're close to being a teenage boy. You sort of look around you, you're outside. What's the first thing you're going to put in sulfuric acid? Okay. One more guess. Ants. Yes. Oh my gosh. That's a former teenage boy. Yes. Yeah. So before I could say, please don't do that, that ant got put in sulfuric acid. It had a seizure and turned to goo immediately. Yeah. So the reason why it did that, by the way, is this is what you can ask your chemistry teacher or professor to do, all right? So if you have sugar and you pour sulfuric acid on it, this is not capturing what it's really like because it's not a video, it's just a picture. It turns into that thing on the right. It goes like totally wild on you. That's kind of what happened to the ant. It turned into this black goo. It didn't heat up, but it was a mess. And the reason is because our DNA contains a sugar molecule, essentially. And so our DNA is, part of it is like this sugar and it just can't survive. So the thought of life in sulfuric acid, it's like this, it's like the ant, it's like bad. But he also put a few other things in, like he did put a leaf, a waxy leaf, a rhododendron, and it didn't do too badly actually. And there's a lot of materials that can survive. And there's a postdoc who was at Harvard, Daniel Dusevich, and we encouraged him to do some experiments. He's part of a larger lab by someone named Jack Shostak trying to make life in the lab. And one of the main people on our team, I'm not trying to name drop, I'm just trying to make sure everyone gets some credit, Dr. Anish Petkowski, they got together and chose some lipids, some fats, and they put it in sulfuric acid, hoping it would self-assemble into a vesicle, and it did. So there are, these materials that can survive in sulfuric acid. And I'm not saying it's a cell, okay? That's like the first step. So yeah, there's a lot of really exciting things going on. Partly motivated by that and motivated by some other things. We asked another team to do some other experiments for us. And they seeded sulfuric acid with a small organic molecule and found that it grew into a rich organic chemistry. And so remember how it's hard, you remember how the UFO talk, it's like the giggle factor? Whenever I think of that talk now, I have to laugh, but there's, yeah, so I lost my train of thought for a second though, so. Okay, right. So there's this sort of paradigm in planetary science that sulfuric acid is dead to any interesting chemistry, right? Yet this team stuck in a small organic molecule and it just evolved into this rich organic chemistry. So they did a bit of searching, and they found that in another industry, it's a well-known fact that there's rich organic chemistry in sulfuric acid. And that's the oil industry, where they use concentrated sulfuric acid to refine crude oil. So we're trying to change the picture here as well. And what I want you to know is that I also got involved in some lab chemistry. And what my team decided to do was to study some complex molecules and see if they're stable in sulfuric acid. And here, what you're seeing is on the left, just look at the picture on the left, it's a DNA molecule. I want to think of the DNA in three parts. The bases that make up the ladder, the nucleic acid bases, ACGT, you've all heard of that. The backbone, and then the linker molecule that links them together. The linker is a sugar, and that's partly where we get into trouble. But what we decided to do was to take these nucleic acid bases and put them into sulfuric acid and see if they were stable. And it turns out, I don't have like the evidence to show you here, but we wrote up a paper, we did all the work, they are stable. So the ant didn't survive, our DNA can't survive. There's at least one part of our DNA that can survive in sulfuric acid. And this is really amazing because it could be that there's a whole set of molecules that could form a DNA-like molecule, but not like ours, but a different type of DNA that might be stable in sulfuric acid. That doesn't mean that Venus can support life, but it does mean we shouldn't be so dismissive and rule it out right away. So what are we going to do about all this sulfuric acid and this idea? Well, we want to get more data about Venus. And I'm really proud to tell you that my team has conceived of a series of missions to go to Venus, to search the cloud particles and search for life directly. Looking for life is still taboo for large government agencies like NASA and ESA, so they have their own missions, but they're not doing astrobiology and they're not looking at the cloud particles. So our first mission to Venus is called the Rocket Lab Mission to Venus. And this mission is launching in January 2025. This is actually a privately funded mission. So it's a small, cheap mission. You can think of it like throwing a rocket Venus. So Rocket Lab will launch a rocket. They'll have electron rocket, the Photon, which is like a spacecraft, will be the cruise vehicle and will go to Venus. And it will drop a probe that's like 15 to 20 kilograms. There's no parachute. It's just going to take an hour to get to the surface. It'll spend 5 minutes in the clouds. So we've got 5 minutes to do our job, and we could choose one instrument. We had 1 kilogram, because everything's miniaturized today, so still good. So this 1 kilogram instrument has a laser, an ultraviolet laser that's going to shine through a window, and it's going to hit those sulfuric acid particles, and it's going to look for fluorescence. Fluorescence excite the molecules if they're there, these aromatics. And if there is fluorescence, we're not trying to say that means there's life there, but it means there's organic chemistry and that is needed for life. So that's what our mission is going to do. We're also going to measure the backscattered polarized radiation to try to say something about what the cloud particles are made of. And that repeats an experiment that was done a long time ago. And if you're interested in learning more of this, we actually rebranded to Morningstar Missions to Venus. That's what we call our missions. Morningstar, it's like Venus is called the Morning Star, something new is rising. We did before call ourselves the Venus Life Finder Mission Study. And you can look up our report if you'd like to know more. There's like this 120-page report, and we have some papers that have been published from this report now. And we did change our name. We had a lot of pushback. Our private funding agencies, we work with NASA to get Deep Space Network time. Pretty much everyone we talked to like heavily pushed on it. So we did change our name, but we're still looking for life and signs of life on Venus. So I'm going to turn to a summary now, and then we'll have time for questions. I want you to know that Venus has many long-standing mysteries. Some were directly measured in the atmosphere by probes nearly 40 years ago. Your takeaway from Venus is that these sulfuric acid particles, they're not sterile to interesting chemistry. They're not like killing everything around it. But there's definitely could be something really interesting going on. There's a new era for Venus exploration now, thanks to phosphine, I think. That phosphine is still controversial itself, but it motivated this whole new flurry of activity. Now, the phosphine story was a bit of bad news for the biosignature gases, okay? Because we found phosphine, people didn't believe the signal, some people did believe it, wanted to attribute to a different gas. If they believed all of it, they pushed back on the non-life sources. Nonetheless, we're still enthused about searching for signs of life by way of biosignature gases on exoplanets. We have oxygen on our Earth, but there are many other gases that might be able to rise to the level that we could detect from far away. I told you about the Webb telescope. We talked about transits. This whole search is really just beginning. The thought I wanted to leave you with is that the search for life beyond Earth is a generations-long search. We're lucky because we're the first ones here who get to try this search. But we're literally going to rely on all of you next generation people, to carry the search on and to have bigger and bolder ideas to make these dreams a reality. Thank you so much. Okay, go ahead. Yeah, we have time for a few questions now. Yeah. So we'll start with Afan.
Yeah, I've asked this question to a bunch of people, and I haven't had a satisfactory answer yet. And it's a very simple question. Why is the sky never green? Because when you go from sunset and sunsets, it goes all the way from red to blue because of radiant scattering, red to purple. But it's never green, because if it goes through the visible spectrum, it should eventually hit green. That's what my thought was.
You mean the sunset?
Yeah, the sunset or any other sky. There we go. It's an atmospheric science question.
Yeah, it is. I mean, there honestly, my sort of gut reaction is maybe there's some, I'm gonna have to think about that, and I'll answer it in a couple minutes, okay? I'll think about it while I get the other questions. Any other questions out there? Okay, shout your question in the backs, and then, yeah.
If you explain something to me that really perplexes me about the Webb telescope, the orientation of the telescope is perpendicular to its orbit, correct?
Yeah, that I'm not 100% sure about that, but okay, do you want to still ask the question?
Well, that's the way I understand it. The sun shield and the telescope is being this way, and looking in one direction. I'm wondering what area of the sky can Webb actually look at?
So you're which part's perplexing you, or you just want to know where it can look?
Yeah, I just want to where it doesn't seem like it can look straight out. That's sideways.
Well, the sun shield okay. I may not be able to answer the question at the level that you need, but the sun, obviously, right, the sun shield just has to be blocking where the sun is. And so it can look, I see what you're saying. Yeah, I think what you're trying to maybe accept is that its viewing range is somewhat limited. Yeah, that's correct.
Can't do this. It could like this.
Well,
Take it like that.
it can't really move that much. Okay, we had a question there in the white sweatshirt, halfway down. Yeah.
I attended your talk in August for exoplanets, and I'm really happy to see the progress after the whole possible development that happened. And I just want to know, are you happy that there are more missions to Venus apart from what, like 2 missions by NASA? There's a mission by India that's in the works. So are you happy that there's more study?
Yes. Yes, very happy. Venus is the new Mars. No. Lots of missions are going. The missions that I hope to lead or am leading, they're very focused. We're just sort of going after the thing we really care about, but we still need the whole context about everything else about the planet. So it's sort of very complementary in a way, because NASA is taxpayers' dollars and everybody has to get satisfied somehow. But then it makes the mission bigger and then it takes longer to build and it's more complicated. But you have a good memory because I was here in August and I was told you about the nucleic acid bases, which we knew the answer to, but it took all that time from then till now almost to like prove it at a level that's needed for the scientific community. Yeah. Okay, question over there in the blue.
You mentioned that you're actually looking at Travis. But you also said that as of right now, can't get any release of other planets without satellite stars. Do you know whether it's capable of providing that data sometime in the future?
Yes, well, we can definitely observe planets around sun-like stars down to red dwarf stars. But the planets we can observe around sun-like stars, they're big planets with big atmospheres.
And terrestrial side ones around satellite stars?
No, we're not. We cannot. And in the talk, I had some numbers there. I think I said it's like the drop in brightness of an Earth-sized planet around a sun-like star is 1 part in 10,000. But then the atmosphere signal, that change, you remember we saw the change by eye? You know, that change would be like 1 part in 10 million or 1 part in 50 million. And that's way beyond what we can do with Webb. It's the numbers just aren't there for us. We have a whole other generation of missions planned or at least conceived of for the future that would use a totally different method to get that job done. It's like if we look at the star by itself, then we look at the star when the planet's in front of the star. We're essentially subtracting 2 big numbers. It gets harder. The more decimal places you need to go to, the harder and harder that is. And the Webb's just not made for that. Yep. Yes.
I know you said that you don't want to rule out the possibility of life on Venus, but do you personally think that there's a chance that there could be life on Venus?
I do. I do believe there's a chance there's life on Venus. Yep. But I believe it's just one we can find out one way or the other. Yes. Yes.
I don't see you. Thank you. I really enjoyed that talk. I was wondering, so you've probably heard of the Imperial mission that'll be launched in the next 5-6 years, in partnership with the ESA. And I heard that telescope will be looking at exoplanet transits around 55 different wavelengths. And they also had a simulation exercise a couple of years ago where they experimented with the use of AI to move the effect of stellar spots and flares from the observations. So I was wondering if you think that this mission has potential to detect things like phosphine and other signals of life.
The question is about a new telescope that's going to be launched from Europe and UK that's dedicated to studying transient exoplanet atmospheres. And alas, that one's not designed to get down to the smallest stars either. It might get lucky to do so, but they're faced with that same problem of the M dwarf star having all the flares and being active and contaminating. Yeah. And I just wanted to get back to the blue sky thing. Like our whole sky is blue because of Rayleigh scattering, and that makes it blue. So we're not going to see green during the day.
Yeah.
And I think, are you asking why don't we see green at sunset when we see all the other colors? Okay, so it makes sense that we should see green. I mean, it's not a primary color, but I guess we do see orange, which is not a primary color either. So maybe it's there and we just can't see it because it's overwhelmed by all the other ones. I mean, I'm going to definitely have to dig into that a bit later.
Okay.
Yes.
You said that your morning star was like privately funded and that it was like a cheap way to basically throw a rocket Venus.
Yeah.
How much did it actually cost to do, and then how did you get it?
Okay, the question is how much is cheap? But before I get to that number, I want you to know that in space, every time, think about it costing 100 times more than on the ground. So for you, if you think like $100 is cheap, you got to multiply that by 100, then it's 10,000, which, wow, that sounds way more than 100. So I'm just trying to manage expectations here. I don't know the actual cost because this cost is split between myself leading the science team and building the science instrument, and I was responsible for fundraising that. And the rocket itself, which is where most of the cost is, that comes out of Rocket Lab, and I don't know how much it costs. And I don't exactly know where they got their money from either. But if I had to guess, if I was going to go and do this, and if I imagined what I think it would be, I'd say between 10 to $15 million. So I don't know if you think that's a lot or a little, but the NASA missions are like 600 million. So, yeah.
Where did you get your private funding?
So the private funding, initially I got some study funds from an organization called Breakthrough Initiatives. And they funded several things. They're funding SETI. They spent $100 million on SETI. And then, like all these missions, they're sort of always like, you're barely alive, like your goal is just to stay alive another day. And then when we did our study, we had this great idea. We found someone amazing to build the instrument. It was his idea to do the fluorescence. It was all great. And then he's like, well, if you don't get money in like 1 month, we can't do it. So I really had to scramble. And then I called upon some MIT alum donors who gave us enough money to keep this instrument going. Meanwhile, we mostly means I had to scramble to like find another source of funds, and then a foundation. They don't like me to advertise who they are right now, but I have to get their permission every time I want to put them on. They did give us money, and they were not like 100% confident we were going to succeed, but they were confident enough. There are private foundations that want to support out their ideas and support this kind of thing. So for this first mission, that's how it was done. The later missions will most likely have to be private-public partnership because it's not really fundable. It was tough. Yep. Okay, we'll take one more question. Yep.
Right now.
Okay, I'll take 2 more questions. You and then. That's okay. Go ahead.
Yep.
No, take you first. Yeah.
Right now you're limited by like 1 kilogram and 5 minutes of exposure time. What would be the ideal experiment for those that more financial limits?
Oh, okay. I like that one. I'm gonna, what would be if there's no limitation at all? And this is, again, I'm planting a seed for someone younger to love this idea because it's gonna be in the future. What we'd like to do is do a sample return from the atmosphere. We wanna go to Venus with a big balloon with a rocket attached to it and collect cloud particles. Some we want to evaporate the sulfuric acid and get whatever's inside. Others we just want to collect the liquid. And we got some money from NASA to study this idea. They do give some money for advanced concepts. We've been working on this. And that would be really complicated. I don't see anyone laughing yet. Remember the giggle factor, because you have to launch a rocket from this balloon that's been floating around in the atmosphere for about a week. And that would come back to Earth. But you know, sample return's a thing now, right? Like with Mars, the rocks are being sequestered for sample return. And there are companies here on Earth that are trying to launch rockets from balloons. So hopefully a lot of that technology can be developed outside, and we can capitalize on that sometime in the future. Okay, we're gonna give the final word to you. Yeah.
I really enjoyed the presentation. Recently, around a month ago, the Canadian Space Agency announced that we'll now be soon having rocket launches on Canadian soil. So, we're in Canada. Do you think that we have a good chance of launching new missions that could potentially have a big difference in the world, possibly with the new launch and so on?
Okay, the question was about launching rockets from Canadian soil. That's fantastic. I somehow missed that. Where's the rocket launch site going to be? Nova Scotia. That's fantastic. And the question is, do I think we have a chance to do something fantastic? I think we do. I think it's like the way the small rocket companies are building rockets now, you know, they're 3D printing parts of the engines, really complicated parts that are hard to piece together otherwise. How everything's like shrunk in size and there's become cheaper. Do we have a chance? I think we do, and I want to put it out to you and the others to make something of that new opportunity. Thank you, everyone.
All right, thanks everyone for a lovely night. Just a couple of quick announcements before we all head out. Before we thank our speakers one last time, we just want to quickly thank the sponsors of this night's event. We literally couldn't have done it without their support. So TD Insurance, MBNA, the Department of Astronomy and Astrophysics here at the University of Toronto, the Dunlap Institute, and the Song of Urania podcast. I also want to thank all of the volunteers at the ASX. All of them are undergrads who put this on, and it's really impressive. So thank you very much. Another undergraduate group that helped out with tonight was the U of T Undergrad Astronomy Union, also undergrads who helped out with tonight. So thank you very much for that. And we're going to announce the raffle winners now. Yes.